Hello, I'm Richard Hammock. Let me tell you about a recent project of mine to design mailing envelopes with non-standard topologies. Let's begin with a standard sealed envelope. Topologically, it's a sphere. You can imagine inflating it like a balloon. It would become spherical. So think of the envelope as a flat sphere. Some envelopes have windows. Such an envelope is a sphere with a disk removed. I'm interested in designing envelopes that are more exotic than just spheres or spheres with disks removed. You'll see that in some of my designs, the window plays a crucial role. It's both a visual device and a mathematical necessity. My first idea was to make an envelope in the shape of a torus. It starts with an 8.5 by 11-inch sheet of paper. I wrote a LaTeX file that's typeset and printed. It looks like this. Then I cut along the perimeter as indicated. Then fold under along this red dashed line so that the bottom edge of the paper folds under and is aligned with the dashed line at the top. Making that fold gives this. Then fold along the central vertical dashed line so that the edges of the two sheets on the right fold under and are aligned with the dashed line on the left. So making that fold gives this. There are two flaps at the left. Those are folded under and glued. The back flap folds in and is glued to the inner sheet, and the top flap folds under to the back of the envelope and is glued. The result looks like this. It's an envelope with a cylindrical pocket with a circular opening at the top. There's a flap along the top here, that you can crimp and fold into the envelope to the inside. Making that fold looks like this. The result is an envelope in the shape of a flat torus. There's no need to use an adhesive on the flap because the double fold holds it in place. You could put a cylindrical letter in it. Here's what the back of the envelope looks like. The recipient of this letter could unfold the flap along the top and remove the letter. Address it, stamp it, and mail it. My next project was a Klein bottle envelope. It's printed on a legal size sheet of paper and cut as indicated. There's a window on the left and notches on the right that will become the neck of the bottle, and down below there are some flaps. This is folded along this red dashed line so that the bottom of the paper is aligned with the dashed line here at the top, like this. Next, fold along the red dashed line here so that this top flap folds to the back and is glued. Then fold and glue these 6 flaps. The result is a flat tube with a slit opening on the right and on the left where these flaps are, and also a window. Fold this along a central vertical dashed line so that the two ends of the envelope meet right here. Then tuck this top part into the window so the two slits are aligned on the left. Next, fold and glue the flaps. Fold the top flap into the top inner sheet and glue, and fold the bottom flap into the bottom inner sheet and glue. The result is a flat Klein bottle. You can see that the tube starts here, it folds over on the right, narrows, passes through the window, and meets itself on the left. There's no need to open it because there's no interior. Address it, stamp it, mail it. What other surfaces can we make? Here's a windowed envelope with a folded strip glued to it. An ant crawling on the surface of the envelope could walk along the strip under the fold and arrive to the interior of the envelope. So this is a one-sided surface. It's a sphere with one crosscap, otherwise known as the projective plane. Notice it does have a hole in it, bounded by this black contour, coming around, going under the strip, and back to where it started. This hole is necessary because the projective plane can't be immersed in three-dimensional space without passing through itself. Adding two strips yields a sphere with two crosscaps. This is another realization of the Klein bottle. Actually, you could add arbitrarily many folded strips. I added 5 strips to this piece of junk mail. So this is a sphere with 5 crosscaps. So you see, you can turn any windowed envelope into a sphere with n crosscaps. By the classification theorem for closed surfaces, you can make an envelope that is any non-orientable surface you desire. But the placement of the strips is significant, as my next example shows. Here is an envelope with a hexagonal window and 3 interlocking folded strips. It has 3 holes, one bounded by a red contour, another bounded by a green contour, and a third hole bounded by a blue contour. Notice that the red-green strip passes through the blue hole, the red-blue strip passes through the green hole, and the blue-green strip passes through the red hole. But this is not a sphere with 3 crosscaps. If you look for Mobius bands, you'll only find one, this pink trefoil-shaped Mobius band. Remove it, and you have a sphere with a disk removed. The 3 holes, if capped, would just glue around the perimeter of the Mobius band. So this is a sphere with one crosscap, also known as the projective plane. You might want to verify this yourself by computing its Euler characteristic. This is in fact a flat variant of Boy's surface, discovered by Werner Boy in 1901. It's an embedding of the projective plane in 3-dimensional space without singularities. Indeed, widen the 3 strips, and the 3 holes narrow into 3 slits through which the surface passes through itself without singularity. And although I could have made the envelope to look like this, with no holes but just slits, I like the version where the bands are a little narrower and the holes are a little wider so that you can see its structure. Address it, stamp it, mail it. This has been a fun project, and it's forever changed the way I view envelopes. I even combed through my junk mail looking for mathematical possibilities. I hope it's changed the way you look at everyday objects too. Thanks for listening. I hope we meet again, and goodbye.